Hi, I'm Keanu, and I'm going to talk to you about my favorite subatomic particles. Let's start with my favorite place, the ocean. There are more molecules in a single gallon of water than there are gallons of water in the entire ocean.
Now let's look at a single water molecule. Within the water molecule, we have 2 hydrogen atoms and an oxygen atom. The oxygen atom's nucleus consists of 8 protons and 8 neutrons, with 8 electrons orbiting around the nucleus. Electrons are a type of lepton, fundamental particles that can't be broken down any further, but we can break down protons and neutrons.
And what we find are the smallest known particles in the universe, quarks. There are 6 flavors of quarks: up quarks, down quarks, charm quarks, strand quarks, top quarks, and bottom quarks. Now we're getting to what I really want to talk about, my favorite subatomic elementary particle, the muon. But where is the muon? What part does it play in all this? Muons don't usually make up matter. That doesn't mean that they don't matter. Muons, like quarks, are subatomic elementary particles, meaning that they cannot be broken down any further. Muons are a type of lepton, along with electrons, taus, muon neutrinos, electron neutrinos, and tau neutrinos. But the lepton we're talking about today only lives for roughly 2 millionths of a second before it decays into an electron and 2 neutrinos. It can travel all the way from Earth's upper atmosphere, deep beneath Earth's crust. Over 100 muons are passing through every minute. That's right, the muon is probably passing through you right now. Muons weigh about 207 times as much as an electron and get their weight from the Higgs boson. The Higgs boson is a manifestation of the Higgs field. It's a fundamental particle that doesn't make up matter but carries force. Almost all subatomic particles with mass have attained their mass from interacting with the Higgs field, including the muon. Everything I've described so far is part of the standard model of particle physics.
The standard model explains the fundamental particles that make up matter and force. It describes how all matter is made up of quarks and leptons,
and how the bosons, the force-carrying particles, influence the particles of mass. The standard model is possibly the current best theory of what everything basically is, but recently scientists have been finding inconsistencies with the standard model. For example, some scientists have calculated a different magnetic moment for muons than the standard model predicts. Muons can be created in 2 different scenarios. The first is in Earth's upper atmosphere, when cosmic rays made out of high-energy particles collide with atoms, sending muons rocketing towards Earth. Muons can also be created in special labs from the decay of pions, which is created by the collision of high-energy proton beams against an MW-class target, such as solid-cylinder tungsten. But how are muons actually useful to anyone? Well, scientists have been using muons to see the atomic makeup inside unusual molecules, and to look inside places difficult to access, such as ancient structures and Earth and even other planets' natural phenomena, including volcanoes, glaciers, and underground cavities. Not only that, but muons have also been used in dangerously damaged nuclear plants to see inside the nuclear reactor core. The future of science is brighter because of muons. Muons matter.